really want to welcome our keynote speaker as chief technologist at Google and highly influential computer scientist of our time. His work has shaped many areas, ranging from theory over information retrieval, data management, and web search to machine learning and large-scale computing, helping define how we organize, search, and reason over information at planetary scale. Before joining Google in 2012, Prabhakar had spent 14 years at IBM Research and later was leading Yahoo Research in Sunnyvale. In fact, what I learned yesterday is that Prabhakar, before he joined Google, this is actually for a German, really hard name to pronounce, sorry for that, turned down an offer from Facebook after a call with Mark Zuckerberg. And I won't reveal why. If you are interested, talk to him. So Prabhakar holds a PhD degree from UC Berkeley and a bachelor degree from IIT Madras. Prabhakar is also a member of the National Academy of Engineering and ACM and IEEE Fellow and a former consulting professor at Stanford University. His contributions have been recognized through numerous awards and honors, amongst other prestigious awards. Prabhakar is also very well known for his textbook on randomized algorithms that many of you might already know. But Prabhakar has also roots in our community. He actually published 4 POTS papers, including a POTS Best Paper Award with Kleinberg and Papadimitriou, and 7 SIGMOD and VLDB papers on topics such as unstructured and web data, contributing to research directions that are now increasingly really important and central to our community. Today, he joins us to speak on can AI assist mathematics and computer science research, and therefore will share perspective on AI not may, but will influence our own field. And therefore, please join me in giving him a very warm welcome and I want to invite Prabhakar here to the stage. Thanks for being here.
Do we get the slides up? Okay, great. Can you hear me at the back? Okay, I'll take that as a yes. So thanks, Carsten, for that very generous introduction. And I want to congratulate all of the organizers of SIGMOD for landing such an amazing conference. And I hope and wish you all the very best in this conference. The title of my talk has a question mark at the end. And for many of you, that may be somewhat of almost a non sequitur, because you say, it's unquestionable that AI can help mathematics and computer science. So what are we talking about? Okay. And I'm going to come at it with a particular perspective. And here's how the talk will be organized. I'll begin with a warm-up setting, which is ongoing work where we're using LLMs to advance our research. Then I'll get to the central portion of the talk, where we'll use a particular LLM-derived tool called Alpha Evolve to prove some results in complexity theory and combinatorics. And then I want to spend 10 or 15 minutes at the end reflecting on where this is pointing, what this journey leads us to, and try and say a little bit about what it might mean for this SIGMOD community. Okay, without further adu, let's dive into my first setting. And this setting is something we call balanced allocations. And it's really about load balancing in planet-scale systems, like Google Search, which was, until recently, one of my responsibilities at Google. And you'll see the theme coming through here. This is joint work at Amar Diwan, who's a Google Fellow in the search team, and Eli Upful, who's a professor at Brown University. I'm going to begin with some facts in classical probability, and then translate it to the setting of load balancing in systems like Google Search. Okay? So here's the classical probability. It says that if you throw n balls into n bins, then some bin is going to have a large load. Okay? But if instead you did the following, as each ball comes along, you pick not 1, but 2 bins at random, and each ball gets thrown into the lighter loaded bin at that moment, then the maximum load is dramatically lowered. Okay? So 1 random choice, bad. 2 random choices, suddenly things get better. And with 3 and 4 and so on, it gets even better. Okay, so here's sort of the cartoon picture. If you throw balls at random, some bin gets big. And here's the application that I want us to consider. You have a stream of requests. Think of this as queries coming into Google search. Okay? You have n serving clusters that could be anywhere on the planet. And what you have to do is assign each query to a serving cluster. Now, critically, because these are user-generated queries, you don't want any request to wait for too long. And if there's a large load at a serving cluster and you send one more query there, then that query is going to take a long time to get served, right? Okay, so this is a process of deciding as each query comes, which serving cluster to send it to. Now, this seems like a clean translation of the probability factor I just showed you, but real life is actually a little more complicated. One of the big things we deal with in Google search is temporal bursts. And these are not as predictable as you might think, but they tend to happen, for instance, in the last 15 minutes of every World Cup soccer game. Okay? One of our most problematic query spikes actually comes from cricket games. And 2 nights ago, there was the IPL final, and that was probably one of our peak load periods, because not only do you have this sudden onrush of queries coming in, but they're also geographically very confined. It's basically the Indian subcontinent, 2 billion people querying for the score. Okay? So when that happens, you don't, for instance, want to send it to the nearest data center, because then your APAC data centers are going to melt down. Okay? All right. Second real-life phenomenon we deal with is that requests come with multiple priorities. So of course, you have user requests, which should enjoy the highest priority. But you also have system-generated queries, which are typically our engineers running eval queries to try and calibrate ranking algorithms. So how do you assign them when in this setting? Okay. Now remember, when I talked about the power of 2 choices or 3 choices, we had this issue that when a query came, you picked a bunch of random serving clusters, and you sent the query to the lightest loaded. But how do you know which one is lightest loaded? Well, you need to know the current load. In fact, in a real system like Google Search, your information on current loads is at least seconds delayed. And this leads to interesting artifacts that I won't be talking about today, but think of it as a control system with a delay in it. So you start to have oscillations and all the things that you used to in a control system, right? All right. So we wanted to study these settings. So faced with this, what does a modern computer scientist do? You write a prompt. And so here's what my co-author Amar wrote. He wrote a prompt. And it says, I want you to explore power of scheduling. I don't want you to read all of this, but essentially it describes the simplest setting. And then at the end, he even says, I have a hard time seeing colors, so please use primary colors, right? And the language model cranks away, and it comes back with a plot that shows if you have one random choice, the average weight for queries is pretty high, the blue line, but otherwise it drops significantly. Okay? Now, I don't want to dwell on this. It seems somehow very easy and magical, but here's something I want you to notice. Amar, and I'm pointing my finger at my co-author here, was kind of sloppy when he wrote the query, because at the top he says power of n scheduling. By the time he gets to the last paragraph, n became d, okay? And n is used for something else. So it's kind of like a professor absent-mindedly telling the graduate student what they do, and the graduate student figures this out and does a great job, right? And imagine if you were doing this in a high-level programming language, you would get a compiler error right away. But these things are pretty resilient. They go off and do these things. All right, so we ran simulations for all of those scenarios, priorities, temporal bursts, etc. And we cranked out a lot of plots. We also proved theorems. And here we had less luck with the language models. So let me give you an example. When there are multiple priorities, here's one of the theorems that we were able to prove. Here the language model struggled. It was able to formulate the right stochastic differential equations governing the process, but it wasn't able to solve them. And in some cases, not all, we as humans overrode the language model and did our thing. So you take all of these plots, all of these theorems, give it back to the language model and say, write me a paper, okay? And it does, and we were getting ready to a conference submission, and we ran into this. So it said, authors are allowed to make light use of language models, but not as part of the methodology or to create a significant part of the paper. And we said, oh, did we create a significant part of the paper? with the language model? It felt to us like yes. So we decided to redo all the simulations by hand. So we sort of threw away all of this prompted thing. But it does raise the question, should archival forums restrict AI tools in science? It's something that I've had a lively debate with John, who was here a few minutes earlier on the stage. And I'll come back to this topic at the end of the lecture. Good. Now let me get to sort of the core part of what I'm looking for. I'm not asking, was AI used to solve some math problem? I'm trying to find signs of AI helping us in ways that conceivably humans could not. Okay? So my curiosity was driven by this paper by Tony Feng and company. And it has a beautifully honest sentence in it. It says somewhere that we had these successes on a so-called set of Erdős problems, but our findings suggest that the problems resolved by us owed to obscurity rather than difficulty. Okay, and I thought this was a beautifully honest statement that they had, that it wasn't that AI did something dazzling that no human could have done. This is something 15 minutes later, some human says, yeah, I know how to do that, right? On the other hand, you have a paper like this, which is more recent, that I think is highly non-trivial. And if you look through the paper, it's a quadratic lower bound on circuit complexity, you suddenly realize that almost, there's a lot of framework that the human has done, but the central hard parts are actually done by the model. So this is sort of a smidgen of evidence that maybe the language model is doing something indispensable here. Okay? And then last week, there was this announcement from OpenAI, which I think is a spectacular piece of progress. So here's the problem, right? You are to place endpoints in the plane, okay? And Erdős asked the question, can you set them up in a way to maximize the number of unit distances between these points? Okay, so you have pairs of points, they're some distance apart. You want as many unit distance as possible. All right, so here's what OpenAI system did, and I don't believe this is one of their generally available language models. They're not clear, but they basically threw a prompt in, a very simple, clear problem statement. And it cranked through, and it came back with a theorem and a proof. And here's what the theorem says. It says there is infinitely many n, not for all n, for infinitely many n, there's a constant delta such that the number of unit distances at least n to the 1 plus delta, which was not something we knew. And this is like a big break. And the system was autonomous in doing this. And I point to this because for 80 years, something like 80 years, mathematicians have been trying to crack this. Okay, so this is a real tangible piece of progress that we have here. Okay, now I'm going to tell you what we ended up doing. So we studied two settings in math and CS. The first is in the hardness of discrete optimization, so it's in complexity theory. And the second is in classical combinatorics, Ramsey numbers. And what I want to say up front, and I'll say this again a couple of times, is the problems we studied are time-tested. They're ones that smart people have looked at for a long time. So they don't suffer from the obscurity that I was talking about. Okay? These are both joint work with Ansh Nagda and Abhijit Thakurta. Okay? All right. So let's look at the first setting, complexity theory. We studied two classical problems, and I'll remind you what they are in a second. One, max cut, and the other is the traveling salesman problem, which is sort of our marquee result in this. Okay? And in both cases, we use an AI tool called Alpha Evolve. I'm going to describe the first result before I get to describing what Alpha Evolve actually does, because it takes a little appreciation for the nature of the proof and the result before you realize what the AI tool is actually doing. Okay, so bear with me. I won't tell you what Alpha Evolve is and how the AI worked until I first show you the first result. Okay, so let me talk about max cut. We have a theorem on the worst case hardness of max cut and also on the average case hardness. And I'll say what each of that means in a second. Okay. So what's the max cut problem? I give you a graph, an undirected graph, and I want you to cut it into two pieces with the goal of maximizing the number of edges you cut. Okay, minimizing is easy, maximum is hard. In fact, it's NP hard. Certainly to find the exact cut, but it's also hard to find almost the exact cut, and that's what we'll try and quantify. And then you can study variants where you're not cutting into two pieces, but 3, 4, 5, etc. And in fact, our very first result that I'll talk about discusses cutting a graph into 4 pieces. Okay? So I want you to think of that. I'm giving you an undirected graph. I want you to break it into 4 pieces with the goal of maximizing the number of edges cut. Okay? All right. So here's what we're able to prove. We're able to prove that not only is it hard to find the largest 4 cut, it's hard to even approximate it to within 98.7%. And that seems like a very quibbly factor, but bear with me and I'll get to the significance, right? So, in other words, if the largest cut has size 1,000 edges, even finding 987 edges, a cut that large, is hard, okay? And the way we do this is through a gadget reduction, and I'll take 2 slides in a moment to remind you what that is if you've forgotten your intro complexity theory class, okay? It beats the previous result of 98.8%. And you say, wait a minute, you used all this AI and all this Google compute to get from 98.8 to 98.7. Yes, these are problems that are in fact well studied. You can see the previous result is over a decade old. And in general, the results that we're improving on are decades old, okay? So it's a small improvement, but it's one that many people have thrown a lot of high-powered mathematical machinery at, okay? So the first thing I'm going to do is remind you very briefly what a gadget reduction is so that you get a feel for what the AI is going to do here, okay? So here's a gadget reduction. I start with a problem that I know to be hard, and here's a problem that I want to prove to you is hard. In this case, it's approximating the max 4 cut. The problem I'm going to start with is called 3 ln 4. It's a family of equations. Every equation has exactly 3 variables, and all variables are 0 mod 4. So everything is either 0, 1, 2, or 3. So I give you this family of equations that you see on the left. This is known to be hard. Please take my word for it. Okay. From that, I want to create an instance of the target problem, which is this undirected graph. So I want to build, you give me this family of equations. I'm going to build a graph and claim to you that if you know how to cut this graph into 4 pieces well, I have a solution to this family of equations. But it's improbable that you could have solved this family of equations, and therefore this must be hard. Okay? So here's how that works. A gadget reduction is a recipe for taking a piece of the source problem, in this case, 1 equation in the source problem, and constructing from it a piece of the target problem. Now, this is a cartoon. This is not actually the graph that you built. Okay? So you want a recipe for taking every equation and building a piece of graph. And when you do this for all the equations on the left and glue together all these graph pieces on the right, you have this big graph. And the claim will be, if you could cut this well, you've solved this. Okay? Everyone got the program? Good. So Alpha Evolve, which is this thing I'm about to describe to you, cranked away for a while and said, here is a gadget that proves 98.7% hardness, okay? And the gadget looks like you take an equation that was on the left, like x1 plus x2 plus x3 is 0, and you come up with this 19-node graph. And the edges have weight between 1 and 1429. Why 1429? I don't know. It's what the machine said. It's a prime number. It's not 1729, which is a lot more interesting, right? But then you say, wait, why do I believe you? How do I know it's correct? Okay, and hold that thought, because proof verification is a critical part of all AI-assisted mathematics. And here we have something, a smidgen of a nice idea that I will share with you shortly. Okay, now this idea of mechanically generating gadgets is not completely new. There was a 1996 paper, so this is 30 years ago, where linear programming was used to construct far smaller gadgets due to Trevisan et al. In fact, it's a bit quick, a strange twist of fate, because this work was done in my group at IBM. At that point, I paid no attention to it, but now I'm paying a lot of attention to it. All right. So now I'm going to describe to you the machine that came up with this gadget. Okay? And I want you to pay attention to one crucial aspect of this. We do not go to an LLM and say, find me a gadget. What we do is go to the LLM and say, write programs that generate gadgets. Okay? So the LLM is stamping out pieces of Python code in our case, a whole bunch of them. And these pieces of Python code are emitting gadgets, okay? These objects. we take these objects and score them by how good an approximation factor they seem to give us in the final proof. Okay? The programs that are doing well, the green programs, we feed them back to the LLM and say, here are the good-looking programs. Give me more of these. And it does that, and it does that, and it goes thousands and thousands of times around. Meanwhile, the ones that didn't give us as good scores, we trash them. Okay? So does that make sense? This is sort of the overall scheme we're going to follow. What AlphaEvolve is doing is using an LLM not to generate or evolve gadgets, but to generate and evolve programs that generate gadgets, which we score by a proxy scoring function. And the successful programs are fed back in to the language model to generate new programs. Okay. Here's one way of viewing what we did. You have some proof of hardness, maybe that somebody else did, but in there is a gadget. You view the proof as a long string. Okay. This is almost like gene editing. You cut out the original gadget and you plug back in a new gadget, and this gives you a better approximation ratio. Okay? In this case, AlphaEvolve found us this gadget with 19 nodes that, if you think about it, seems improbable that a human would have found. And I'll come back to this point later. Now, I highlighted to you that you need to verify that this gadget actually delivers the claimed theorem. Okay? And the right way to do it is to exhaustively take the gadget, cut it in 4 ways in all possible manners. And this is a process that takes hours. Okay? But we want this thing to crank thousands of times through an inner loop, so we cannot afford to take hours for every verification. So what do? We go to AlphaEvolve and say, find programs that do the verification. Okay? And that's what we did. So we created a synthetic data set with lots of graphs of 15, 20 nodes, and said, AlphaEvolve, print out programs that will verify 4 cuts in these graphs. Okay? And we give you only 1 second in which to finish it. Now, that's a system constant we chose arbitrarily. But we figured that if we could verify a gadget in a second, we could afford to go through several thousand times in a run. Okay? And we had to play some other tricks. We used a language model to critique these programs. But at the end of it, we had these verifiers that seemed to do the job. And I'll tell you what I mean by seem to do the job on the next slide. Okay? So AlphaEvolve has created this verification program. It seems to do a verification in a second. We are cranking it through, spitting out these gadgets. And you're still suspicious because you're saying, well, you said it seems to do the job, but how do we know that the gadget is actually correct? Okay? And here's what we actually did, right? So for 4-cut, for instance, it devised its own branch and bound strategy. The LLM wrote a branch and bound strategy. It did lots of system-level optimizations using libraries in Python that we didn't even know existed. Okay? And it gave us about a 10,000x speed up over exhaustive verification. Now, exhaustive verification is not something anybody wants to do, but what used to take several hours to do the verification, it would give us in 1 second. Okay? But I cannot today tell you that these verifiers that we used to prove all these theorems were actually accurate. Okay? So then why should I claim a theorem? Because at the end, when the final gadget was stamped out, we ran it through a day-long process to get an exhaustive verification. So you see the schema. In the inner loop, you use fast and sloppy verification. You spit out what looks like a proof. And then at the end, you do an exhaustive verification. And in this case, the exhaustive verification is really only for the gadget because the rest of the proof is held intact. So we just have to make sure it fits in nicely in the gene-edited form. Okay? Does that make sense? I cannot see if anybody is saying yes or no or anything. So these lights are amazing. Okay, so let's take stock of where we are, right? So AlphaEvolve doesn't use an LLM to generate proofs. It uses an LLM to generate programs that generate proofs. Okay, it's a single-shot run. So we write a prompt, and then we sort of sit back and say, go do your thing. Okay, we are not interacting and saying, well, how about you try this and how about you try this? Is absolutely autonomous, right? AlphaEvolve doesn't really know I am proving hardness for this theorem. It's been given a proxy scoring function by us, which we crafted. But that's all it's going on. Okay? And the gadgets are fast verified, sloppy verified, to help us keep going. Otherwise, we would have never gotten these results. We would have run out of time. So, finally, there's a lifting process. So although we construct a 19-node gadget, the theorem that results holds for all n. Okay? Just like all reductions, basically. All right. I'm now going to touch briefly on a couple of other results in complexity theory that were obtained in a very similar methodology. Okay? So there's a family of results we have for both max cut and maximum independent set, which are two classical hard problems. And they all are of the form, if you take a random graph, how close to the best answer can you come? And essentially what we're able to say is modulo certain mathematically unlikely events, okay, because all of complexity theory is relativized in this sense, right? You cannot, for instance, certify a max cut within 5% of optimal. Okay, and this builds on earlier work of Kuniski and Yu. We also use analysis to show that this is essentially the best possible. So here's a case where AI is kind of closed off a small research area, okay? And the way it works is similarly, you do a gene editing style. You take the Kuniski-Yu proof. In there, they had these Ramanujam graphs of about 10 nodes with certain properties. And we used alpha eval to find far larger Ramanujam graphs. I won't bother telling you exactly what a Ramanujam graph and eigenvectors and all of that stuff, but you plug it in, and out pops a theorem, right? Again, there was fast and sloppy verification involved to make the loop go fast. Now, let me finish the segment on complexity theory by talking about the traveling salesman problem. Most of you know what it is, but I'll quickly remind you what it is. Salesperson must visit n cities. We assume they sit in a metric space. Okay? It's NP hard even to find an approximately good tour. So the best known upper bound, there was an algorithm from 60 years ago that got a 3/2 times optimal. That was improved to 3/2 minus epsilon about 5 years ago by Carlin and company. And the epsilon is like 10 to the minus 38. Okay? So it just says you can just get below 3/2, right? And now, in contrast, what's the best we can show is hard. We can show, Klebik and Klebikova, about a decade ago, did this piece of work, finally appeared in 2020, that said getting closer than 117 over 116 is NP hard. So what's that saying? If the shortest tour is 116, then even finding one of length 117 is NP hard. Okay, that was Klebik and Klebikov. What we were able to do is to improve that to 111 over 110. Again, you're going to squint it and say, is that really an improvement? Yes, it is. Because in general, you want to keep pushing this factor up. It's conjectured that the right answer is 4/3, but you can see both from the upper bound and the lower bound, we're not close to this. Okay? So this is a very well-studied problem. In fact, the first paper on this is from 1991 by Papadimitriou and Yanakakis. And they just showed that approximating is hard. They didn't even have a constant. So over the last 35 years, we brought it up to 111 over 110, which is our result. And the schema of the proof should look familiar to you. It says, take the proof, replace a gadget by another. But there's a bit of a twist here. The prior work did not have this clean formulation of here's a gadget, you just improve it and you're done. So we had to take several pieces of work, including Klebik and Kapinski et al., and come up. So this is a case where the humans did a lot of the work, felt a little bit like if you have in the wet lab, a very expensive piece of equipment, the human does a lot of cleaning. That's kind of what we did. And then gave it to the machine, and the machine came back and said, use this gadget. Now one thing I'll point out in this gadget is if you stare at it, it doesn't have the three-way symmetry you might expect in a Mod 3 gadget. And there's a little bit of significance to this I'll highlight at the end of the talk. Okay. Now, I'm going to touch for a few minutes on Ramsey numbers. I believe most of you will have come across Ramsey numbers at some point, but it's this beautiful piece of combinatorics. And it goes back essentially 100 years. And Frank Ramsey had this observation that if you invite 6 people to dinner, then you're guaranteed that you either have 3 mutual friends or 3 mutual strangers, okay? So in other words, given enough size, no matter what the chaos is, order will emerge, either in the form of a clique or an independent set. So in other words, if you take the complete graph on 6 nodes, bicolor the edges, you're either going to have a red triangle or a blue triangle. That's what Ramsey said. Okay? And we're going to denote that at the very bottom of the slide as R33 equals 6. And then this led to this rich field of Ramsey theory where we studied the following. Given two integers, two positive integers, R and S, what is the Ramsey number of R and S? Okay, how do you find the Ramsey number for R and S? Well, in general, we don't know. And there's sort of a cottage industry in discrete mathematics on finding upper and lower bounds. What I'm going to tell you now is how lower bounds are found. They're typically done computationally. Okay? And the computational goal is the following. Suppose you could find a graph. You could build a graph on 35 nodes and say, well, there are no 4 mutual friends and no 6 mutual strangers. Then you know that R46 is at least 36. Okay, does it make sense? Good. I'm assuming you're nodding. I can't see. So here's a table of Ramsey lower bounds found computationally by AlphaEvolve. How does AlphaEvolve find them? It takes a cell, it writes a program to try and generate graphs of 35 nodes or 91 nodes or whatever, right? And comes back and says success in some cases. This picture is about a month old. Since then, we filled in a few more cells. Let me explain all the colors to you. A blue cell is one where AlphaEvolve found a lower bound, and that is the best possible lower bound because it's a matching upper bound. Okay? In all of these cases, the lower bound found by AlphaEvolve is not new. It matches something that we know already. Okay. And we have about, half a dozen of those. Yellow cells are cases where AlphaEvolve found a lower bound that does not match a known upper bound. So the upper bound is higher. But that lower bound was already known. Now, think about it for a second. Just because you matched the lower bound, it doesn't mean you found the same graph that found the lower bound. It's some graph found the lower bound. Okay? The green cells are all ones where AlphaEvolve now holds the world record. It broke the previous known record by anywhere from 1 to 4 in size. Okay? So those are things that new lower bounds we found. Let's take stock of this for a second. I mentioned that for each cell, AlphaEvolve is printing out a program that finds that lower bound. In fact, it's printing out thousands, and then one finally broke through. I didn't want to bother showing you raw code, so what I did was I used Gemini to summarize the code. And it's kind of curious to look at a couple of these search algorithms. And I want you to imagine there is one for every one of those cells. In fact, we put all these on GitHub so you can look at them if you really care. Right? So algorithm 14 was the lower bound for 3,11. Okay? And it says, well, we are going to start with a diverse pool of starting graphs, like Paley graphs and this and that, and then we're going to do something called adaptive scoring. Now, none of this is done by a human. This is all done by the machine. Okay? We're going to flip edges, and we're going to do this fancy form of simulated annealing, where if we get stuck, we raise the temperature again. And it comes up with a bound that matches the best known. Over to the right, it's doing this for the cell 3,13. And here it does something completely different. And this is one of the characteristics. The fact that it found a certain lower bound here says almost nothing about the lower bound approach for the next cell. Okay, these things seem to be rather independent. Okay? So, just to summarize some of the observations, so every cell seems to be harder or easier, depending on the number theoretic characteristics of R and S. And we tried hard to find common threads in all the successful programs. We failed. Okay? But the meta algorithm AlphaEvolve, which came up with all of these algorithms, is common to everything. So it's in some sense a single universal algorithm, but it does use language models and its knowledge and understanding of Ramsey theory that is in the language model and of algorithms and heuristics to come up with these cases. Right? And if you read them, what it seems to be doing is taking natural approaches that humans have found and piece them together to come up with these successful approaches. And in one case, there's something like 6 cells that were in that table previously found, where there was a mysterious project in Russia that came up with graphs that proved the lower bounds, but didn't say at all how they came up with these graphs. So we have no idea. We were able to recover those lower bounds, and we publish the algorithm. So now, researchers can look at how those cells are derived. Once again, there's a fast and sloppy verification you can do, because what happens is, as these algorithms are cranking, they're building these graphs and saying, oh, I still have 73 cliques, I need to bring it down to 0. I have 47 independent sets, I need to bring it down to 0. The numbers are usually much higher. And it turns out you don't need an exact count. You can do an approximate count, and AlphaEvolve comes up with these approximate counters that are very, very, very fast. Right. So now for the last part of the talk, I want to reflect a bit on where we've come, the journey till here, and what it might say for the journey ahead. Okay. So where would these results rank among research results I would be proud of? Well, as original research, probably not my favorite, but the significance here is not what these results are, but how we got to them, and the extent to which autonomous language models got us there. Okay. Our use of AlphaEvolve is somewhat syntactic. We are not pretending the language model deeply understands what it's doing. It is coming up with this fragment of a proof because we told it to. Okay. Potentially, better models endowed with better semantics should do a far better job. And in fact, some of the newer systems we're building are doing this. Proof verification, I think this is a critical bottleneck in any such autonomous system. And the learning here is being sloppy in the early rounds is perfectly okay, as long as you're rigorous at the end. Now, you say, well, could a talented human have produced these results? And some of you may know the story of André Weil, the famous mathematician, who says he did his best work when he was imprisoned for 6 months by the French authorities and completely isolated, right? So maybe if you took somebody who really knows the subject and locked them up for 6 months, they could come up with these things. But it seems hard to believe that a gadget of 19 nodes with all these weighted edges is something you could come up with paper and pencil, right? I'll also remind you that the TSP gadget exploited asymmetry, and this is new because all the previous gadgets that people had considered for the TSP hardness were symmetric. But ultimately, I think the right measure is, number one, are these problems that a lot of people have worked on, the test of time? And number two, are these problems that where you publish a result and 15 minutes later somebody doesn't come up and say, yeah, I did the same thing by hand, right? And if not, there is some evidence that AI played a critical role in this. Okay. You could say, well, take a smart person, give them the same amount of computing you had. Could they have done it? And again, it's hard for me to prove to you that, beyond reasonable doubt, that this is impossible. But let me give you a suggestion, right? We tried things like SAT solvers and SMT solvers. We threw a computer algebra system at it. And the numbers, at least as we were able to encode them, was rather daunting. Some of these problems, the number of constraints was over 10 to the 300. Okay. Now, of course, you could say, well, I have a friend who's really good at math programming, and they would have cut it down. And absolutely true, right? So I'm not claiming that we were absolutely state of the art, but it felt like traditional tools like math programming would be inadequate for this today. We started wondering, what is AlphaEvolve actually doing, right? So you have this LLM that's unleashing a fleet of programs. Today, people might call them agents, right? And they're evolving code to generate programs. So this indirection seems to help, okay? And one way of thinking about it, and an interesting way, especially if you're a faculty member, is you now have 10,000 graduate students assisting you. And you can say, you, John, you're going to work on this Ramsey cell, nothing else. Now, in the system we built, John working on a cell is not talking to Mary working on a different cell at all, right? That's sort of an independent run. Okay. This is very evident in the Ramsey search. Okay. But we don't have a real understanding of why it wins when it does win. Okay. You can say, well, why didn't you just prompt the LLM directly? Well, for the balanced allocations work, the load balancing work at the beginning, yes, absolutely, it did help with the simulation. So this differential equations that came up, we couldn't get direct prompting to work. And for the rest of the talk, when I talked about complexity theory and combinatorics, we couldn't even sometimes get the model to reconstruct the state of the art, let alone get to something beyond. So I think there's a need to enhance the zero-shot prompting with some form of guided tree search through many pieces of code or agents or whatever you want to call it. Okay. Now, here's an observation that we realized along the way. Language models are rich in success stories. They've been trained on successful papers in mathematics, computer science, whatever. Failures don't make it into a language model. They sit in your heads. So all of you as professionals have a lot of experience. So, well, I tried that. I know it's not going to work because of this. That never makes it to a language model, right? So one of the things I think it's going to be important is to try and encode in the search process notions of failure that have to be unlocked from the heads of humans. And you could probably do that using some form of reinforcement learning with humans and so on. But that's something we're still thinking about. But this, I think, is an important observation to understand. Failures aren't in language models, or seldom in language models. Okay. So one of the things that led me to think about is, what is the process of doing mathematics? Okay. And there's this beautiful essay by Bill Thurston from about 30 years ago. And he argues that the job of a mathematician is not to crank out theorems, but to deepen human understanding of mathematics. And you have to wonder, well, if I had a machine crank away for days and weeks, and it comes up with, behold the answer, is that deepening mathematical understanding? And I'm not sure. Now, some of the more recent proofs, they spit out these things called thinking traces that arguably help you understand what the machine did along the way. Okay. But I think this is a very powerful viewpoint that, that should be understood. Should LLMs be banned from archival science? I think the genie's out of the bottle. This is obviously my biased perspective. You already have one Nobel Prize that wouldn't have happened without the power of machine learning, and that's AlphaFold for protein folding. Right? So we went from it taking 5 or 6 years for a student in a wet lab to determine the 3D structure of a protein to 200 million proteins being 3D folded in a matter of weeks. Okay? Weeks may not be fair because it took a lot of human thinking to design that system, so all of that goes into it. But still, it didn't take 200 million years. Okay? So, and I think the argument is a bit moot because we did not ban previous generations of scientists from using microscopes or telescopes. And likewise, I don't think we should be banning them from using LLMs. Right? Now, when I was talking to John, he said, well, but what if people claim false results? And indeed, that's a concern. But as an author, you take responsibility for the correctness of your results. So if you publish a paper saying, here's my result, then you're stuck with it, right? But there are clear concerns, okay? Just in terms of some trends, if you look at data from about 4 months ago, approximately 20% of CS papers now show significant markers of LLM-assisted writing. Now, you could say that's just the writing, it's not the real research. The line is hard to define. But one thing that people repeatedly say is that in LLM-assisted writing, the conceptual density is not high. There's not a lot of intuition. And instead, it's smooth and confident and fluent writing that doesn't necessarily convey much. And that's definitely not a service to the community, going back to Bill Thurston's comment. Okay? In fact, Archive has implemented stricter controls because there's a rash of review papers. It became very easy to use LLM to write a review paper, get heavily cited, your H-index goes up. Nice. Right? So there was an explosion of low quality. So these are genuine concerns that the community has to triage. Because if you start to stamp out lots of entirely LLM-generated papers that may or may not advance scientific understanding, then you're stuck in the position we are in today, which is a lot of LLM-assisted reviewing. I don't know if Carsten and Sudeepa tried to measure how much of the SIGMOD reviews were LLM reviewed. Okay. So I'm going to net out this part of the talk and close with some reflections on what this might mean for SIGMOD. Right? So LLMs are becoming pretty commonplace for web research. But is there a definitive capability beyond humans that AI provides? Is there the equivalent of Move 37 in the second game between AlphaGo and Lee et al., where human Go experts looked at it and said, yeah, that doesn't seem like something a human would have done. This seems truly exceptional. Okay. Sloppy verification of proofs, I think, is here to stay. Right? And this indirection, not directly prompting an LLM, but going through these agents, seems very powerful. Okay. All right, so what does all this mean for the SIGMOD world? And here's a very personal look at how I've seen the world of SIGMOD evolve. Now, there's sort of the obvious thing you could do. An LLM is really a rewriting system. So one form of rewriting you can look at is SQL query optimization, or any query optimization for that matter, right? So there's already promising early investigation. I see papers even in this conference that touch on this, right? So given a SQL expression, you have to rewrite it, make it go faster. But of course, you're stuck with the problem of verification again, because is the rewritten query going to get the same results as the original one intended? Okay. But beyond that, that's sort of a very tactical thing we could be doing. But where does the arrow of time take us, right? If you look over the last 75 years of computing, here's my view. In the beginning, everything was very structured. It's basically data that came out of a physics lab or a space orbital thing. 25 years later, the enterprise sort of took over. You have the RDBMS with classical enterprise applications. But by the year 2000, by the time we all got networked, suddenly there was this explosion in unstructured data, because you have billions of people generating email and web pages and all of this stuff. And we had this conundrum where almost all of the volume was unstructured, but almost all of the value was structured. And we collectively, in this community and others, spent a lot of effort writing entity extractors and things to try and pull out those pearls of wisdom from the sea of unstructured data so that you could recoup the value in them, right? And curiously, around the year 2000, a little after, this was solved not by a computer science algorithm, but a market mechanism. Essentially, what we did was we abdicated the job of extracting the most critical entities, words, phrases, to a market which bid on keywords and phrases and created $1 trillion marketplace that underpins the economy of the web. Okay? And so this was the first time, in some sense, computer science and microeconomics came together in a very amazingly seamless way to solve a CS problem, but using economics. Okay. Now, in this era of LLMs, what we're having is systems like AlphaEvolve and its successor that I'll give you a glimpse of in a second, that are stamping out these agents that are spitting out voluminous traces of quote-unquote thinking, lots of text, right? And we have to make sense out of this. And I noticed that one of the awardee videos actually touched on this as well. Okay, so here's an evolution of AlphaEvolve. Essentially, what you have is the picture that looks like before, but now the agents, instead of ignoring each other and doing their own thing, are looking at community blackboards and trying to understand what other agents are saying and doing as they get through it. And I'll give you traces, snapshots, of a system we have right now that we're just developing. This has already broken some Ramsey records, and we're learning. This is still early stage, right? So this might say, final breakdown, here's the optimal approach, and you start with this, and this is one agent spitting it out. And in this case, what actually happened was we got a new Ramsey lower bound because one agent claimed there was an approach, but said they was giving up, and then some other agents picked it up and said, oh, I know how to finish that off, and did it. So there was some collaboration between multiple programs that came up with this, right? It's also the case that every now and then, an agent would spit out something that was complete nonsense. I found a huge breakthrough because they feel very stressed, I think, about having to make progress. And they'll make these claims, which sound like tweets from some politician sometimes. So it's kind of neat how it goes. So here you are trying to make sense out of this, right? So essentially, you can spin up a system with interacting agents that evolve. Okay, the verbosity is okay because they're not trying to be structured. They don't have a rigid schema, none of that, right? the data they emit will be voluminous and largely unstructured. Okay? The interpretation and action on these traces that are spit out, that are emitted, is left to other LLMs, right? It's not bound by humans' ability to consume the sort of megabytes that are being spit out, right? So I think this, for the SIGMOD community, means you're upon a new era of active or agentic unstructured data. This community has made a transition I've seen over the years with the amount of content dedicated to unstructured data increasing over time. And now you're in this new agentic unstructured data. And I thought, I'd give a little gentle suggestion here that I made that go away because I didn't want you to take it too seriously. But it's a potential evolution of it. So for me, we're in a ferment. We're in a very tumultuous area with a lot of things changing around us. And this is super exciting as researchers, as Carson said at the beginning, for computer scientists at large, but scientists at large, right? And I want to close with a classic line that I found in this paper by Alan Turing, where he talks about the imitation game. And at the end, he talks about different forms of learning. But he has this amazing sentence at the end. We can only see a short distance ahead, but we can see plenty that there needs to be done. Thank you.
Thanks, Prabhakar, for this wonderful keynote. And we have 10 minutes left for asking questions. There are microphones in the room, so feel free to step to a microphone and ask your question. So, I see Felix already moving to a microphone. So, Felix.
Yes. Thank you, Prabhakar. Great talk. I have a quick question. When in the scientific process do you think one should involve LLMs, or when are you allowed to start using them, both at a single project level, so how deep do you need to know about the problem, and at an educational level, so at what level maybe in your education should you start using LLMs?
Oh, wow. I think we are so early in this journey that there's a lot of experimentation going on, both at educational institutions and in industry. It's probably fair to say that we still are feeling our way around. Like even in this research, you can see how tentative I feel about even the successes we've had. On the one hand, I feel good. We took time-tested problems. We threw LLMs at it. We got something out of it. But I don't yet feel like I can give you a cookie-cutter recipe that says, well, stage 1, do this, and stage 2. I think we're still years from that. And part of the reason is we also have this tension between general purpose models that are still evolving very, very fast. But one of the things when I was adapting these models to products that I was building, like search and Google Maps and so on, is if you try to customize them for a particular application, like one of these products, by the time you finish the post-training, et cetera, the mainstream model has already gone up. So in a sense, for the moment, I would say keep your faith in the mainstream model and then come back to specialization by application over time.
Okay, thanks.
To do some load balancing here with a simple algorithm, I go to the center queue.
Thanks for a great talk. So I'll ask the obvious question. Right? It's great to see all these results coming from you guys, from OpenAI. They all seem to be using closed models, really high resources. Where do you see sort of the role of, is the mathematical or TCS research going to be now centered at these places? How do you see as academics getting access to things like this?
I think this is a good question. I'm more optimistic than you sound. And the reason is that AlphaEvolve, this thing I showed the results with, is already about 2 years old. It is not state of the art, right? The OpenAI unit distance result was, I would think, pretty state of the art. But I see a lot of AlphaEvolve-like systems, in some ways better systems, coming out of universities. There's one called EvoX coming out of Berkeley, right? So universities are embodying these ideas very fast. And so really you can take the commercial off-the-shelf models together with really nice systems ideas to build better proof engines. I don't think you have to have everything, like infinite compute essentially and the state-of-the-art model. you can make meaningful progress in academia without having all of the goodies. So I'm optimistic, and I already see that coming from many universities.
So go to the right queue.
Good morning, sir. I am very much convinced with the thing that AI can assist humans in research for science and mathematics. So, and as a student, I agree with that also. My question is very common. I would like to see what you think that as of now, AI is assisting us in science, research in science and mathematics. But as fast AI is growing, is in near future, can AI replace humans in research in science and mathematics?
I don't think of displacement and replacement as a primary concern. I did a little bit of research into the kinds of essays and editorials that were being written in the year 1830, which is roughly 200 years ago. And the language they're using is almost exactly the same as we use today about, oh, we humans are going to be useless and get displaced and so on. That's not what came to pass. What comes to pass is humans over time adapt dependably into doing new kinds of activities. So your role as a researcher, as a scientist, will likely be different from what we were doing 10 years ago. But it's not like you will have no role and you just sit back and let the machines do their thing. That is my belief.
Thank you, sir.
So let's do a bit of unfair scheduling and go back to the center queue.
Hello, Prabhakar. So I'm curious to hear your thoughts on AlphaEvolve itself. There's lots of work going on, including in my group on something called Darwin that's similar. I think of it as a genetically as a LLM-flavored version of genetic algorithms.
Sure, good.
What's your thought? Any deeper insights given how much you have played with it?
I don't have a deeper insight, Raghu. I think your description is pretty spot on. The only insight I would add is I think this form of simple architecture with an LLM stamping out, and evolving programs is probably passé at this moment. We have to think more. And in particular, the first step we've taken is not to isolate the different agents, but to let them communicate. And this is where this common blackboards and how do you make sense out of it? How do you distill what is real from things that they claim? That becomes super interesting.
If I may, just to follow up on that, let me be more pointed.
Yeah.
If you look at the genetic generation and evolution of candidates which are then scored and so on and so forth, in any flavor I've seen today, there's distinctly missing an element of a rigorous search space, which you see in prior things like simulated annealing, right? And why? Why haven't we made that connection yet?
Okay, so I think those of us working in the area, and presumably your group, we do actually think of this as a rigorous search space. Even in the case of multiple agents, these are massive search spaces, number one. Number two, they don't have clear gradients in many cases. So you have these agents sitting around. You don't have this notion of one of them saying, I'm getting pretty warm. Everybody else, come on over here, right? And so the gradients are very gentle, right? And I think one way to ameliorate this is the comment I made that you have to be able to bring in failures much more, because in any machine learning problem, having only positive examples doesn't get you there. Having negative examples is important. So I think that is an element that has to come in here pretty critically. I'm not sure how we do that without a lot of humans sitting and spending their time interacting with these things. But somehow we got through that with AlphaGo, through reinforcement learning, and I'm hopeful that we can do something similar here.
So let's go to the left queue.
Hi, thank you. Thanks for the talk, it was great. You mentioned that telescopes and microscopes were used by scientists before to solve problems, and now we're using LLMs. Those were solving anatomical problems. So are you saying LLMs will also solve the same section of problems?
So I meant that as a metaphor. Like, we did not hold up astronomy saying, in fact, this is a current issue. The most powerful telescopes are not available to most astronomers, right? Because there's like half a dozen of these things in Chile and Hawaii and so on. And if you're looking at certain forms of the spectrum, you have to be at one of these telescopes. But there's plenty of astronomy. 99% of astronomy happens outside these telescopes. And in contrast, LLMs are available in spades to many researchers. Everybody in this room can get one. You don't have to be in Chile or wherever to get a state-of-the-art LLM. So in that sense, I think these are broadly applicable and more broadly available. That was my metaphorical point.
Thank you.
Let's go back to the center queue, which is long.
Prabhakar, you talked about fair and unfair use of AI. Now LLMs write better text than most of us, and many people are saying that the research object by which we'll be judged as researchers should not be a paper. We should stop writing papers. What we should be creating as a research output is the code, the data, some other structure, the protocol, whatever it is. And then if we want to read, these humans to read it, press a button and then a text comes out. So how does the publication process, the whole research cycle changes with the use of AI?
Right. This is a great question. One of the things you may have seen, many of you probably have seen videos by Terence Tao, the famous mathematician, who talks about how mathematics should now be encapsulated and submitted as a lean proof. And then, as you're saying, John, it can be instantiated as an explanation for a human.
By the way, people know me as Yanis. So you made reference John, but that's okay.
Sorry, Yanis, whom I've referred to as John. The thing is, in Tao's universe, everything is captured in a lean proof. It's a little early to take that step. I'll tell you why. The best lean compilers, for instance, can handle a few thousand statements. And that's not going to do for Fermat's last theorem, let alone someday in the future, Riemann hypothesis or something like that, right? So I think we're building up these tools to your broader point, right? If I throw a whole bunch of code out there and data, do we have the machines that can consume it intelligibly for different audiences? And I think we have to build up that infrastructure.
Great, thanks.
Let's go to the right queue.
Thank you for your talk. My question is about the line between what humans can do and what LLMs can do in mathematical proofs. You mentioned lean, right? And even in data management, we have work on verifiable data systems in which we use theorem proving for query correctness and so on. So do you think these methods, theorem proving, would you could apply the same techniques because you go very much on generating some instances. So would this be possible?
True. And in fact, there are rich strands of work parallel to ours where the verification is done by a lean prover. Remember, though, that today they are still pretty slow to compile and prove an assertion. And this is where I think we got further because we were willing to take sloppy and potentially incorrect verification, but that's very, very, very fast. And we could crank much further. I think lean still has a ways to go. So let me put it this way. If you insist on formal verification at every step, then the depth to which you can go is likely limited. Does that make sense?
Yes, it does. Thank you.
Okay, in interest of time, I would close the question and answer session here. And Prabhakar will be around, I guess, also a bit in the coffee break if you want to reach out to him, ask the remaining questions maybe while you have a good cup of coffee in your hand. But what I want to use at the end is to thank you again to be here and to share your thoughts with us. I'm wondering how the talk would look like if you give it in a year, because we are advancing that fast. So let's see what the future brings us. At the end, we have a short present for you for giving the keynote. And I like to ask the general chairs to come up with a present to hand it over.
Wow. Thank you.
And a big applause again.
Thank you.
Try out how this works.
You're going to do that?